This video, we're going to prove the following lemma. It says that a finite integral domain is in fact a field. That is, if you're an integral domain and you're finite, bingo, you're a field. Nothing more to show after we prove this. Can use it unless you prove it. Talking about proofs, if you like watching mathematical proofs, then subscribe to my channel. Before we get into this, let's recall what an integral domain and a field is. Doesn't have to be finite. What are these objects? Okay. So, an integral domain is a commutative group with no zero divisors. What does it mean, no zero divisor? For example, if you have, say, 7 times 2, which is 14, well, that equals to 0 mod 14. When you divide this by 14, when you divide this number by 14, the remainder is 0. 7 is not 0 and 2 is not 0. But when we multiply them together, we do get 0. That means 7 and 2 are 0 divisors. If you do not have 0 divisors, like in an integral domain, that implies that A is 0 or B is 0. And this is in an integral domain. If AB equals 0, then one or both of those numbers is 0. A field, on the other hand, is also a commutative ring with a unit element and multiplicative inverses. So, what do you need in a field that we don't have in an integral domain? Well, they're both commutative rings, but a field, it has a unit element and inverses. So we need to show that if you're a finite integral domain, there's a unit element and there are multiplicative inverses. So let the proof really begin here. Let the integral domain D be the set x1, x2, all the way up to xn. So it has n elements. And also, let A not equal to 0 be in the domain. That is, it's one of those. Now, consider the following set. Consider D prime, where every element in D gets multiplied on the right by A. So we have x1a, x2a, all the way down to x sub n a. Now, this also has n elements. That's the first one they're counting for us. That's the second element. That's the nth element. And I claim that D prime has n distinct elements. That is, no two elements in here are different. Okay, so suppose for I not equal to j that xia is equal to xja. I can bring this to the other side and I'll have that xia minus xja is equal to 0. On the right hand side of each term I have an a, which I can factor out on the left, on the right. So I get xi minus xj times a is 0. But we're in an integral domain. We know that that's not 0. And the only way the product of two things can be 0 in an integral domain is if one of them is 0. And it is in A. That implies that xi minus xj is 0. Bringing the xj over, that implies that xi equals xj. But that means I and j are in fact equal. And that's the contradiction. We suppose that for I not equal to j, that there were two elements in D, or two different elements in D that were in fact equal. And we found out no, we're wrong. So the claim has been established. D prime has indistinct elements. Well, okay, so now for xi and D, we have that xi is equal to xja. That is, xi maybe is equal to x1a or x17a for some xj in D prime. Actually in D, excuse me. So let's get rid of that prime. But since A is in D, where did we say that? A is in D. It's not 0. Since A is in D, A must equal to one of these elements in D prime. So A is equal to xi times A. But we are in a commutative ring, an integral domain. We're starting off with a finite integral domain, and we want to conclude that it's a field. So it's a commutative ring. Now, it's always commutative in addition. So when they say a commutative ring, they mean that the elements compute, or maybe I should say also commutes under multiplication. So this here is the same as xi times A. Wait a minute. I multiplied A by some element and I got back A. I multiply A by some element and I got back A. It's reasonable to ask, is A the identity element in D? Either it is or it isn't. Okay, so let's take an arbitrary element in D. Well, that implies that y is equal to, let's call it xja. Okay, so we want to show, oops, typo, not if A is the identity element, but if xi is the identity element. Okay, so let's see. Let's take y and multiply it by xi, and let's see if we get back I. Well, y is the same as this. So y is xja times xi. But this is using the associative law. This is xj times axi. But axi, when I went to use the commutative law, I didn't commute. I'm sure you all caught that. axi is A. So this is xj times A. Ooh, look at this. xj times A is j. So I took y, I multiplied it by something, and I got back y. So xi equals 1, let's call it 1, is the identity element in D. Okay, so we showed that this finite integral domain has an identity element. Now I need to show that it has an inverse. Okay, well, 1 is in D. 1 in D, that implies that 1 is equal to A times xk, and it commutes, which is xk times A. Well, that implies that the inverse of A is xk. Now, everything I did from here down, I can pick a different element in D. I can pick a different element in a non-zero element in D, meaning that there exists an xk for every A in the ring D. Okay, and this is for all A in the domain. But it depends on what A is. I'm not saying that B is in the domain, that B inverse is xk. I'm not saying that. So you know what? Let me say it differently. So this implies that there exists an inverse for all A in the domain. Hence, D is a field. And that completes the proof. If your finite integral domain, you now can say, oh, this integral domain is actually a field. Okay, you have to prove it before you can use it. Thanks for watching to the end of my video. Please like and subscribe. Leave a comment. Don't forget, family and friends and enemies need to be told about my channel. See you guys hopefully in the next video. Watch and learn.